force transmissibility is where I'm concerned about like weak connections, and I'm worried about the force that will be transmitted through a vibrating system, right? So the force transmitted to the mass is the sum of the force applied by the spring damper combination, right? So from a free body diagram, right, we can show that F of t is equal to k x minus y plus c x dot minus y dot, right? Those are my forces going up to the mass, right? We're just taking out our mg's because they cancel out. Where this force is countered by the inertial mass, right? How is this force being counteracted? It's being counteracted by the inertial mass of the system, which is F of t is equal to negative mx double dot of t. So only consider the steady state, right? That's all we care about. Again, we know from before that x of p is equal to omega n of y times the square root of omega n squared plus, 2 zeta omega b, that whole term squared, over omega n squared minus omega b squared, that term squared, plus 2 zeta omega n omega b, that term squared, cosine of omega b t minus phi 1 minus phi 2. If we differentiate this twice, right, so we can get we get x dot of p, and then we can get x double dot of p, and combine with f of t is equal to negative m x double dot of t, I guess. We can get that f of t is equal to m omega b squared omega n y times the square root of everything we had under there before, right? And then the same cosine term, cosine of omega b t minus phi 1 minus phi 2. I mean, we could rewrite it, but I don't think it's super important. Now, again, I want to get this as a ratio of my forcing function to my natural frequency. So I am going to insert R equals omega b over omega n. And I'm going to get an expression that we will write. So as, let me write it like this. So capital F of t, my forcing function as a function, my forcing as a function of time is equal to capital F subscript t. Just going to break that out. Cosine of omega b t minus phi1 minus phi2. And now f of t, f of subscript capital T, is equal to ky r squared square root of 1 plus 2 zeta r squared over 1 minus r squared, that whole term squared, plus 2 zeta r squared. Again, this can be converted to a force transmissibility to provide a normalized response such that f of t over ky equal to r squared 1 plus 2 zeta r squared over 1 minus r squared plus 2 zeta squared, that whole term squared. So now what I get is my normalized force over my stiffness in the system multiplied by my amplitude of the excitation going into the system. And in a plot, that looks like this. Right. So what's important here? One, you'll notice that I can get a lot of force for an underdamped system at resonance.